I'll take off where I finished yesterday. So, like just a short refresher about stochastic turbulence and the mimicking. Said, in order to construct a stochastic interpolant, we fix a coupling phi of our target nodes. Then we sample random vector according to phi. Then the stochastic interpolant on T, nothing but a random bridge with random endpoints given by x. One. Whereas, so this is as called random bridge. At that time, the noise driving the bridge should be thought as independent of the noise or the randomness we use to generate phi. So this process, as we said, has the right margin at time 0.1, but unfortunately, it's not Markov. And moreover, we would like to improve somehow the coupling between 0 and x1, have something that is more expressive. So then we try to compute the Markovian projection. What does it mean? So we try to compute the drift T such that if I take the law of the diffusion with initial distribution mu and drift B, and I look at time T, well, then I get exactly the marginal distribution of the stochastic interpolant at time. Theorem is that this drift actually exists, and you can write it down in closed form as a conditional expectation. Theorem states that the drift x equal to expectation of one essentially the mimicking drift is a randomized version of the drift associated with the Brown function. Randomized in the sense that here we take an expectation and we condition on xt I equal to x. If this is deterministic and equal to y, then we get back the drift of the Brown bridge with fixed endpoint. So I think I would like to give a little bit an idea about the flavor of the proof. Maybe I will not do all the calculations, but at least tell you a bit how it goes. Okay. Okay. So in order to do the proof, let me introduce a last piece of notation. So I will introduce the transition density. So yesterday it was Orstein-Uhlenbeck, now it's Brownian motion, but it changes. So proportional to its exponential minus, let me check about the 4. There is 4. Minus x. And I will introduce, so we'll assume for simplicity that pi has a density against Lebesgue, but at the end this doesn't really known. But by doing so, I can define a sort of renormalized version. So now I will mix up pi with its density as usual, and p tilde is just inverse of the transition density at time 1. Multiply. So why do I do this? Because with this notation, I can have a relatively convenient expression for the marginal distribution of my stochastic interpolant. So recall the idea was I sample from pi initial and final distribution, then I join with the bridge. So the density of the bridge at time t, you just find it, I mean, by conditioning. So you take the joint density at time 0 t1, divide by the marginal. And therefore, I think it should not be too surprising, but in case we can discuss this more, that you have this expression here. So you integrate what pt at 0x, and you have t1 minus t. That's 1. And okay, maybe to be more pedagogical, now I should divide by this term to get the density of the bridge and integrate against pi. But I use the tilde to write up something slightly less on the board. This is pi tilde, ex0. Maybe, okay. I think this is probably a better thing to do. This is I sample pi and then I sample the Brownian bridge conditional, and I integrate. And now I just want to absorb this guy in here because this guy does not depend on x. So when I take, and does not even depend on time, so it's just some sort of constant when I take the solids. Okay. I mean, I don't need to be quick at all. So if there's any question, just okay. So now I'm going to do something that might look a bit strange in the sense that I will first find a velocity field with which I can represent the density with a deterministic OD. This is a bit strange at first, but it's something that people often do in even in optimal transport. When, there's this nice connection between gradient flows and Brownian motion. This is more or less this idea. You can view the marginal flow of the Brownian motion as a deterministic flow generated by a deterministic vector field, which contains the gradient of the entropy in the process. Anyways, there's no need to go into this complicated story. I will just do the calculation. So in order to do the calculation, I will need some information on the behavior of my heat kernel. This is, of course, the heat equation, right? Well, not maybe write X and Y for spare notation, but I should precise that the time derivative of the heat kernel is either the Laplacian taken with respect to X or the Laplacian taken with respect to Y. The analyst, there's 1/2 is. No, there's no 1/2 because I paid the price of a 4 here. So I have a square root of 2 Brownian motion. In the end, if I miss some 2 at the end of the proof, we will fit, we'll do some regression and see. But I guess it's really without 1/2. Okay. So of course is this is the classical Kolmogorov equation, and the fact that you can swap x and y is just because the heat kernel is symmetric, x and y. So change everything. Okay, so now let's differentiate. So of course I allow myself to bring the derivative inside the integral. Here I apply the product rule. Here I just remark that I swapped the time direction, so we get minus Laplacian. Okay, and I will of course absorb this one into pi to get a p tilde. So the first thing I can write, this is equal to the integral of. So I have Laplacian with respect to x now of pt. Now I will not write all the arguments, otherwise I don't have enough space, but we want to size of times t. Then I have minus t Laplacian always with respect to x of t. This is the first iteration. And now I do something. So I add and subtract gradient pt, gradient p minus 1 minus 2. Okay. So if I do this, okay, the plus goes together with this guy, the minus goes together with this guy, sorry, as you may imagine. So if I do this and I do some chain product rule again, I find myself with the integral of the divergence x. I just rewrite Laplacian as divergence of gradient. That's it. What? So the first term is gradient x pt 1 minus t. And the second term is minus e gradient x 1 minus. Again, I just use the fact that divergence. I just use the formula of the product formula for the divergence. Correct. You can just think of this calculation in 1D. Should be pretty straightforward. But of course, I may do mistakes, so please help me. And now, well, I authorize myself to take the divergence out of the integration because I'm integrating with respect to x0 and x1, and the divergence is with respect to x. And then I do another thing. I divide here by pt. So I have to multiply by pt. And here I divide by p1 minus p. So I have to multiply somewhere, like here, by p minus. And this starts to be pretty, starts to take some decent shape because let's see what happens. I take the divergence out and I write my integral. And then I observe that I can factorize p1 minus t pt because it's in both terms. So then this guy here is grad log pt. And this guy here is minus grad log p1 minus t. Of course, here you start to smell the conditional expectation because grad log p is again. is a divergence. So what I've shown I've shown that if I define Vt is a velocity field, I will explain maybe 1 second why it's called velocity field. Vt as the inverse of the density times this object here. I will change the sign, please see why. Then I found a solution of the so-called continuity equation for the density of the interval. Is this? Of course, I'm not finished yet, but I have a first representation of my flow, because this is a bit of an excursus, but it makes sense even from a machine learning standpoint, because it's yet another way to represent the flow, and people do use it in practice. So let's pause a bit the proof, because we want to represent this with an SDE, but this is already telling you by the well-known relation between continuity equation and deterministic ODEs, that if you consider this deterministic flow, x dot equals dtx, x0 distributed according to mu, then the push forward of xt after mu. So the flow is deterministic, but since the initial point is random, the law of xt is still random. So this is my stochastic interval. This is the well-known relation between continuity equation and ODE flow. So there is no Brownian motion here, essentially. And you see that in some sense we are reassured, because we don't want to see this guy. In my drift, there is only this guy. So now we have to do something pretty classical. So we have to kind of convert this equation into the equation that describes the density of the stochastic diffusion, classical diffusion, which is of course the Fokker-Planck equation.
Should be defined without the divergence.
Ah, sì, there's no divergence.
It's
Yes, it's without it. It's without it. Okay. Yes, it's without it.
and the minus
No, the minus should be okay, right? Because this has a minus here, but you have to bring it on the other side. So this should be okay. So I have to transform my continuity equation into a Fokker-Planck equation. I know that the Fokker-Planck equations correspond to marginal flows of stochastic differential. So let's do just that. And maybe here I've got all the computation. So you can check that if you define pt of x as pt of x plus the gradient with respect to x of log of EIT of x, then you can transform this into a Fokker-Planck equation for the drift E plus drift part and phi minus Laplacian x equal to 0. This is just algebraic manipulation. You use the fact maybe just to show that when I plug this term here and I multiply by PIT, what I get is the divergence of IT that multiplies gradient log PIT. And you see that this is just the divergence of the gradient of EIT. And this is the Laplacian. Standard trick to. So okay. So the thing that you need to check in order to finish the proof is that the drift that I defined here coincides exactly with the drift that I defined in the statement of the theorem. Okay, that's the last thing that remains to be checked. Maybe I'll do it because I think it's one calculation. You do it once and you see how things work. It's gonna be shorter. Maybe I keep the expression of the velocity field. Just one remark, you already see that the velocity field already admits an expression in terms of a conditional expectation. I just need to somehow cancel the part of it. Okay. So we have to compute essentially this thing here. So we start by computing this thing here. Well, here I do nothing clever. Just bring the gradient inside. So this is going to be integral x e minus e plus 1 minus e x e tilde. And again, I want to see only grad logs, so I write this as the integral of x log pt plus px log p1 minus e T1 minus T by tilde. It's just chain rule. I mean, I haven't used any PD. And then if I divide by PT, PIT, I get this expression multiplied by GI e to the minus 1, which looks kind of nice because it's exactly this thing here. The only difference is that here you see I have plus plus, and here I have plus minus. So this term here is gonna, because now remember that my drift, I have to sum the two terms. So this guy here is killed by this guy here. These two guys, they sum with the 2. And now is the hour of truth because I don't want the 2 in the end. So let's see. So this means that let's write the full expression for finish. I have 2 times one, and now unfortunately I'll be able to write all the arguments, but you know how they are. This is just by summing the 2 things. And now I just need to conclude. But we are more or less done, luckily. Because if you think about it, well, essentially, this is already a conditional expectation. Also, you see that x0 has been, there is no x0 anymore in the thing I'm integrating. So actually, I'm only really integrating against the law at time t and 1. You see that the integrand, x0, is gone. It's exactly the effect of adding the grad log. So the part with x0 in the integrand is gone. So actually, I can already write this as, I hope it was clear. What I'm saying is that I just can integrate out x0 to kill this term and get a 1. So I can already write this as the conditional expectation of the 2 times conditional expectation of grad x log E1 minus E xit xi1, knowing that x I is equal to x. Now I'm done because okay, now I have the full expression for the heat kernel. Okay, and here you see that luckily I had a 4 because when I compute the gradient, I pick a 2, so I get a 1/2 that kills this guy. So this is exactly the drift I want. So I will not write it, so we don't really fully check it, but it's okay. So we have computed the drift that can be used to replicate the flow with the Markov process. Right? Well, I mean, I will supply lecture notes where the calculation is laid out in even more. And of course, in practice, as Alain has discussed, you don't, I mean, to compute the drift, you just obtain samples from the joint distribution and minimize the empirical version of the loss that you get from representing the conditional expectation as an L2 projection. Okay? I think maybe we don't have to go over this again because Alain has discussed this a few times, but it's in the lecture. The bottom line is that you don't compute it, so you compute it pretty much in the same way where in which you compute an approximation of the scope function. Not really any conceptual difference. Okay, now I would like to first let's see how the algorithm looks like. So the algorithm is, as I called yesterday, diffusion flow matching. Maybe okay, I'll start right here. So it's a generative model essentially that corresponds to the Markovianization of the stochastic interval. It's called diffusion flow. So maybe just a little bit of history. Have been proposed, I think, around February last year, something like this. I don't know the exact name. It's fun.
In fact, there is a couple of guys, Lippmann.
How do you write it?
L-I.
Lippmann?
Yes.
Okay.
And one of his students. And banana claim, Algarve and banana claim.
But okay, and others. Don't worry. And there's a relatively extended survey online. If you Google stochastic interpolance, you will find it. 70 pages about millions of variants of this. And it's mostly methodological, so it's mostly about how actually to use this algorithm in practice and what kind of results we can get. So sometimes it's a bit of orthogonal thing I'm doing here. But okay, how the algorithm would work? Again, what do we need to have as an input? We need our coupling. And we need, we need a choice of interpolant. We will take here the Brownian bridges. And thanks to these, we get, a theoretical expression of of the drift. And in practice, of course, you will have approximation of the drift on the partition of the interval 0, 1. That will be known by S star of T, K, and between 0 and capital N. It's a partition of 0.
So also here, the partition is not equally spaced, but you have a finer mesh at the beginning and then less, like no.
There is freedom. You can, yeah, and anything you want. But then, yes, it doesn't happen. So but okay, here there is a bit of a difference in the sense that the measure mu and the measure nu, they are more or less on the same level. It's not, before, you have the Gaussian, the pure noise, and then the data. Here it's not so clear. So maybe the general principle would be it has to be fine at the beginning and at the end, and you can be, but also okay, another thing, you cannot be too sloppy even in the middle, because here we want to interpolate over 0, 1 fixed. And one of the rationale, so the rationale behind it is also that you want to avoid the computational burden of having a long time interval. So I don't know about practical implementation. I'm sure Alain knows more, but I would say you cannot be too wide even in the middle. Okay, so we have score approximations. Sorry, we have approximations of the mimicking drift, and then we can do our algorithm. So we start with the data, or with mu. Sorry, we don't even know what it is. And then we do our Euler scheme in between. So x e is equal to x ek plus the approximation of the drift. So s star a that we compute at x k by h plus b minus h and t square root of 2. So this is better. This is of course for all t in the interval ta. H is the difference. Maybe I should have written just to H is just. This is really just Euler discrimination of your stochastic function. Okay. Yes, theoretically. Sorry. Just discretizing, taking the Brownian increment between t, k, and t. Yeah, in the end, I wanted to use this to save some space. It was a great idea, anyways. Just Euler discrimination. So that's how the algorithm works. And maybe one interesting thing is that unlike score-based diffusion models, where there's quite some literature on the theoretical guarantees for the algorithm, for flow matching, this is not that much. So it's still quite open how to prove that the low at time one of the algorithms that we use is not that different from new of the low you'd like to get. It's still not very clear. Okay. And then also,
What did Lippmann do?
oh,
Just
they proposed the algorithm.
the algorithm is just the standard.
Yeah, it's mostly about having the right idea. I mean, of coming up with the algorithm. And of course, okay. I mean, you have to realize that the BT that I wrote before is actually the tricky one. So let's say it's somehow two not separate words, but there are two different tasks. One is come up with an algorithm that works and that shows nice results, and the other one is to try to understand why. So these things go hand to hand, but not in the way you write papers. So you first start with the algorithm, then people try to see. Okay. Sorry. So I did a little. It was a bit confusing, maybe the notation. I hope now it's clear. But if you have questions, yes. Okay. If there are no questions, I would like to move on to, let's say, this the last part of this first lecture, which is about connecting this algorithm with other algorithms that are very popular in machine learning and that stem from the study of the optimal traffic. So let's somehow not forget, but let's somehow take a high-level view of diffusion flow matching and see what it does in abstract terms, say. Because this will suggest us a new algorithm that has also been proposed. This should be around November 2023, something like this. And then I will try to, I don't think I will manage to convince you, but I will try to just give the intuition on why this new algorithm actually connects all the problem related to optimal trade. stands for. So in very abstract terms, we can view diffusion flow matching as a procedure that goes as follows. It takes a coupling. Let me call it phi, and let me put a 0 now. It generates a stochastic interpolant. From the stochastic interpolant, you compute a Markovian drift that mimics the interpolant. And then, then you compute your process X star, which is actually the process that you get by approximating the drift, doing time discretizations. Now, suppose we are in an ideal world where you're super good at approximating the score, and actually, instead of simulating X star, you're able directly to simulate the Markovian diffusion given by PT. Okay, of course not what it will. But suppose for some miracle, you can sample this. Fine. Then here it's a bit tempting to do the following thing. Say, okay, I have diffusion. Let's look at the law of the diffusion at time 0 and 1. This will be again a coupling, because this diffusion mimics the interpolant, which has the right margin. So you see that I can close a loop now. Of course, by the way, this coupling here, of course, maybe I should also write the whole. There is no reason that this law here coincides with pi 0. Actually, it will not. Of course, because it's a Markovianization of pi 0. There is no reason. Fine. Then I get a new coupling. So then I can iterate. I have pi 1. I construct a stochastic interpolant. I compute the Markovianization, and I keep going. One could wonder where does this converge? So is it clear? I mean, I just so I start from pi 0. I have my interpolant, I have my drift. I'm in a nice world where I can actually exactly simulate the Markovian drift. I get a new coupling, not the original one, and the idea is okay. Now let's repeat.
Sorry, I forgot why the new coupling is different from the original one.
Simply because when you take the Markovianization, you preserve the marginal flow, but you don't preserve correlation between the positions. So you preserve the law of x0, you preserve the law of x1, but you don't preserve the conditional distribution. That's exactly what Markovianization. So you get a new one, and this means you can iterate. And you may wonder, if I keep iterating, do I converge somewhere, or is this getting super wild? So maybe let's try to write this in form of an algorithm. The algorithm actually has a name. It's called diffusion. No. I think it's diffusion Schrödinger bridge matching. Diffusion Schrödinger bridge matching. It's a bit of a spoiler. We're going to converge, but I will explain what I will not explain now the name. I will explain it. So what does this algorithm do? Well, suppose you have computed your coupling phi n. Well, I just put indices over. Suppose phi n is given, then you sample. You consider a random vector x n 0, x n 1 below is phi n. Then you construct the stochastic equivalent. So you just take the Brownian bridge between x n 0 and x n 1. This you define it to be, define it to be your nth stochastic equivalent. And then you compute the Millington drift. Well, according to the procedure, just the conditional expectation. I will not write everything. And then you set En plus 1 below of x mu n 0 x and then you're. And then, so the idea, the overall idea is that we thought that each time we do Markovianization, we get something better and better and better. So in the end, we should get something that minimizes a certain criteria, certain cost. And indeed we do. And let me present you what we're going to get in the end. Detailed proof for two reasons. First of all, a rigid detailed proof does not exist at the moment. That's a good reason. So it's sketched in some works in a very simplified context, or maybe, yeah. But there is good. I will give you a good intuition, hopefully, on why one expects this to be true. I don't give the proof, but one day there will be a proof. Okay, let's make a little detour. Let's introduce yet another topic. So what is entropic optimal plan?
Sorry, that's another stupid question. So after the first step, aren't we Markovianizing something that is already Markovian, or?
Yes, I hope nobody would ask. Yeah, so you do. But you have to keep in mind two things. First of all, it's not clear that remarkovianizing gets you the same result. Okay. But also you have to keep in mind that
Clear is not true.
Huh?
I think it's not true.
And then there is another thing: is that in true implementations, you will always have to discretize this. So this will not be Bn. This will be the diffusion flow matching associated with the drift Bn. So in any case, this operation will not leave the process invariant. You really do something. Okay. Okay. I hope that this addresses the.
Yeah.
So
you said that when you reject process, you get.
You don't necessarily, yes, you don't necessarily keep the same. In fact, okay, maybe another comment, because in fact, the drift that I compute is one drift that makes that allows you to represent the flow with a Markov process, but there are many drifts. So even in the choice of the Markov process that you use to represent a flow, you have a lot of choice. Even if you keep the sigma constant, you have lots of choices, and you need a criteria to select. For example, if you were in the deterministic setting, when you try to interpolate with ODEs, the criteria that you use is to minimize the L2 norm of the velocity field which gives you exactly optimal transport. And here the idea is that in the end, iterating this Markovianization will choose a drift that that minimize a certain cost or criteria, which is exactly the one related to entropic optimal. Okay. All right. So it's again a lot about entropy, as most of the things we've been saying in the course. So let's introduce. So R0T, I keep my notation that R is the law of a reversible Brownian motion. Well, it's a law of the Brownian motion. So this is just the proportion. Okay. And what I try to do in entropic optimal transport, I try to. So H is always Kullback-Leibler or relative entropy. I say I want to find the best approximation of the joint law of a Brownian motion at times 0 and capital T among all couplings or of two given distributions. Okay. If you want, it's a constrained version of the energy model that Alain has presented. I guess the statement is pretty much clear. And why it's called optimal transport? So let me, no, maybe I'll do it. Let me recall the standard optimal transport. But optimal transport is a similar problem in which you try to find the coupling of your marginals that minimizes the quadratic distance, the average quadratic distance. This is the standard optimal transport. And this is the entropic optimal.
Excuse me, but R03 is not a probability.
Yes, it's an infinite, it's a positive measure. So again, I could take, I could make it a probability measure. It wouldn't change. Okay, maybe there are reasons why I would like to keep it like this. In any case, it's not a problem because you can define relative entropy against positive measures. There is a way to do it. But okay, if it's traveling, really, it doesn't change anything. Let's put a Gaussian here. And here I can put whatever up. So the two problems are strictly equivalent, actually. They have the same optimal solutions. Doesn't change. All right. So, I mean, intuitively, you can see that there is a relation between the two because when you compute relative entropy, you have to compute the log density of your coupling against R0T. And if you take the log of this density, there is a quadratic term coming. Okay. And more or less, this the log that you get here corresponds to the quadratic term that you get here. It's not super obvious to make the link rigorous, but the rough idea is that when capital T converges to 0, so the time horizon over which you set entropic optimal transport converges to 0, then you have that entropic optimal transport with time horizon capital T, sorry for the correct notation, converges to, in some sense, optimal. Also, if you do large deviations, it's some sort of infinite dimensional version of the Varnadans formula, the one that tells that going from X to Y in short time, you go along the geodesics. And more or less, this is the same thing, because maybe I'll try to say a few words later on why it should be the same thing. But you just a even more heuristic analogy is that you can view essentially this optimizer here as a sort of asymptotic log probability of a system of Brownian particles who is asked to go from U to U. Okay. But I will not elaborate too much on this because we are not doing small time asymptotics here. We want a fixed capital. But if you want to know more, feel free to write or reach out. There is a huge literature about this limit nowadays. But for me, the connection with optimal transport is more to just to somehow give more motivation about this problem. I will not really use it in some slides. Okay. All right. And I told you yesterday that stochastic interpolants are reciprocal processes, and these processes are pretty old. And this is also very old. So actually, this problem here goes back to 31, 32. And it has been introduced by Schrödinger. In fact, in the more probabilistic or statistical mechanics literature, it's not called entropic optimal transport. It's called the Schrödinger problem. So what Schrödinger wanted to do, he had the following question. I have independent Brownian motion with initial distribution mu. I look at their configuration at time t, and I see that the configuration looks like mu. What was the most likely evolution of the particle system that allowed the configuration to go from mu to nu? He did not have this tool at the time, but now we kind of can put this problem into a rigorous formulation using large deviations. It's Sanov theorem. And in fact, you see, for those of you who like this kind of things, the relative entropy is the large deviation rate function associated to Sanov theorem. So if you think a little bit about it, if you want to find the best way particles can use to go from a configuration to another, you minimize the corresponding large deviation rate function among all possible evolutions which correspond to the couplings. Okay, this is actually how I personally came to study this problem. Again, I don't want to develop this perspective here because it's a bit it's not really related to machine learning. But if you're curious, I'll be happy to say some more words. But again, the funny thing is something very popular nowadays for algorithmical purposes actually is an odd problem. Okay. So the heuristic that so by now it's no surprise is that the sequences of couplings pi n that I have produced by iterating flow matching converges to the optimal coupling in the theorem that pi n converges to pi star, which is optimal in time horizon 1. Put a T here. Okay. It's not at all clear why this should be true from the sketchy description of the algorithm case. And in order to maybe grasp the intuition on why this should be true, I would like to introduce one last algorithm to today's lecture. Yes, there is not. So it's 20 minutes on. Yeah. Which is yet another algorithm to compute the optimal coupling for this problem here. So the algorithm I'm going to introduce is called the Sinkhorn algorithm. And it is also an algorithm that has been very popular over the last decade or so in machine learning. not necessarily in connection with generative models. Because let me tell you maybe a couple of words on why. So why would you be interested in solving this problem from a machine learning? Sorry.
So the convergence, pi n goes to pi star, which kind of convergence?
So as I said, who knows? I mean,
Who knows? Okay.
no, I think you can have, there are some rigorous results in this direction about weak convergence, because essentially it's not too difficult to show that the entropy of pi n is bounded, so you immediately have some compactness. This is kind of understood. I guess if you're a machine learner, what you would really like to know is the speed of convergence. This is completely open. It's very difficult to understand. But yes, let's say weak convergence to be on the safe side. Yeah. So why would you care about solving this problem if you didn't come from generative modeling? Because in optimal transport, you often in machine learning, you often care about solving optimal transport for millions of reasons. You want to compare images, whatever. You often care about computing the distances. Even Alain has given examples of situations where you may want to compute this distance. So Alain also has explained that after discretizing, this is just a linear program. So linear optimization problem, and you have tons of solvers for it. But there is one thing with linear problems, they're not convex. And you like to solve convex problems better. For example, because they have a unique minimum, strictly convex. And relative entropy is a strictly convex function. And since when t is small, this problem is believed to be, so actually is a very good proxy for this problem, one reasonable thing to do is to say, okay, I don't want to solve this one, too complicated, because it's not strictly convex. I make a small convex regularization, and actually you end up with this one. So from this standpoint, it makes sense. But of course, the natural question is, okay, thanks, but you could make any convex regularization. Why do you pick exactly the entropy? Because you could regularize with a square function, whatever, and here you just go with x log x. And the reason why entropy is so popular is precisely because you can deploy synchron algorithm on this problem and not on other convex regularization that you may come up. And synchron algorithm is known to perform quite well in the computation of optimal couplings. So I would like to just tell you a little bit about this algorithm. Compare it vaguely with diffusion Schrodinger bridge matching, and then try to get from this comparison why you could expect that Pn goes to star. So maybe last thing, why now we kind of know why the algorithm is called diffusion Schrodinger bridge matching, because this coupling here pi star is called Schrodinger bridge because it comes from Schrodinger. All right, so let's talk a little bit about synchron. And even this algorithm has been known for 60 years or so, much before people in machine learning started to really understand the potential of it. But of course, starting from the moment when, like some 10 years ago, when people really understood it's really efficient for solving this problem, has received a tremendous attention. I think the original papers by Synchron should be around the 60s. There is even earlier works about this. Okay. So to motivate the algorithm, let's see what's difficult here. So the difficulty here is not really entropy minimization, is to fit the marginals. So one thing you could do is to say, okay, let's consider, instead of the set of couplings, which is difficult to project on, let's consider the set of probability measures on the product phase that do not fit both marginals. They just have the first marginal, which is correct. I don't ask anything about the second. And in the same spirit, you can define just the set of probability measure on the product space that just fits the second. This way, the set of coupling is just the intersection of the two. And the idea is that if I were just to project on, or to replace the set of couplings with one of these two simpler sets, then the solution is basically free. I don't want to go into the details of this, but the minimization becomes very, very simple. But after discretization and everything is just summing numbers and doing coordinate multiplication of vectors. So let's take for granted that the problems in which you try to approximate anything, not just R0T, any probability measure on the simpler sets are very easy to solve. This is the only thing I want you to keep in. So the problem is, of course, the final goal is to optimize among couplings. So if you fit only one marginal, the other one will be wrong. But then what would you do? You just alternate between projecting on one set and projecting on the other set, and you continue. And in the limit, you should get something that fits both margins. And then it's going to be optimal. That's exactly how synchron algorithm works. So start. Now I've coupling over two indices. One index counts the projection on the first set, and the other index counts the projection on the other set. And you start with the, actually initialization is important here. You start just with the reference measure. This you know how to compute. R0. And let me maybe put a bar just to differentiate between this coupling and the one produced by Diffusion Schrödinger bridge matching, because of course they're not the same. And then suppose we had computed E bar and N. First solve. First find E bar N plus 1. N, which is just the best coupling in the same problem where we replace the constraint set. So we just project on one marginal. And we replace this guy with the former coupling we used. Then, well, without much surprise, you compute P bar N plus 1, N plus 1. by projecting on the other set with respect to the P bar form. And you iterate this. This is synchronous. Again, the idea is that these problems are super simple to solve, whereas the problem when you project on the couplings is very difficult. You iterate, and after many iterations, you can hope to be very close to the optimal coupling here. So this algorithm, as I said, is pretty popular. It's known to converge exponentially fast. It has been known for a long while that it converges exponentially fast the optimal coupling if you operate on a compact space. So if your measures are not measured on RD, but measured on some finite space or compact space. But actually, for the kind of natural problem, for at least for the type of applications we are targeting here, which is quadratic optimal transform, it's really tricky to understand the exponential convergence. But there has been some progress, and for this, I would refer you to Giacomo in the audience, who has written part of his PhD in showing actually the exponential convergence of the algorithm in the unbounded case. All the results that were available for finite state spaces, they would have exponential constants that dramatically depend on the diameter on the space. So there is no way they would scale to unbounded spaces. And somehow this is a bit frustrating if you think about the fact that, first of all, okay, quadratic optimal transport, so the one which corresponds exactly to this case. The natural one, for example, in view of the algorithms I just presented. And if you consider the fact that if you take Gaussians as marginals, you can explicitly compute all iterations. It's painful, but you can fully detail what's the coupling of any iteration. And you immediately see that there is exponential convergence. But when you get out of the Gaussian world, somehow, of course, nothing is explicit anymore. It's really not clear how to get exponential convergence. If you want to know more, again, I would refer you to Giacomo for further information. Okay. So let me end by comparing this algorithm with diffusion Schrödinger bridge matching and trying, hopefully, to raise some intuition on why diffusion Schrödinger bridge matching should converge to the same gap. Okay. So, if you think a little bit about it, both algorithms alternate between projections. In Synchron, it's clear. Synchron alternates between projecting projections on the set of measures that only fits first marginal, and projection on the set of measures that only fit the second marginal. You do ping pong until convergence. It is very clear. But even DSBM alternates. This is maybe not so clear. Maybe also because I didn't explain that well. So if you recall, at each iteration, we have a coupling, and we compute a stochastic interpolant. Actually, you can view this operation as projecting the law of the diffusion onto the reciprocal class of the Brownian modes. Let me be more clear. So you recall I said that reciprocal processes have a nice property that their bridges are the same as Brownian bridges. When you make the Markovianization, this property is lost. There's no chance that the diffusion process that you've generated will share the same bridges with the Brownian motion. So this property is restored as soon as you construct the next stochastic interpol, because again, you will use the coupling of the diffusion and connect point with bridges, so you will restore the property of having the same bridges as the Brownian motion. In other words, maybe let me write it more clearly. So the nth stochastic interpolant has the same bridges of the Brownian motion, right? Because we construct it like this. We take the coupling and we join point with bridges. So having the same bridges as the Brownian motion means that you are in the reciprocal class of the Brownian motion, which I called yesterday calligraphic R. Just means bridges are equal to Brownian bridges. And then, so we can view the step of creating an interpolant from a coupling as the step of projecting the diffusion, which is behind the coupling, onto the reciprocal class. Because we kill the diffusion property, but we get the reciprocal processes out of the diffusion. So you project on the reciprocal class. So you should think at iteration n-1, I had a drift bn-1, which gave me a Markov process. I take its law at time 0,1, and I construct a stochastic interpolant. So I kill the Markovianity, but I add Brownian bridges. That's what you do. So you can think that this operation is a projection on the reciprocal. And then the other projection that you do is the one I explained a bit better, is the Markovian projection. So you project on Markov. Okay. So both are going to keep projecting between different sets. Is this clear? I can elaborate a bit.
I actually understood that every time you were projecting on Markov process.
Yeah, this is better. And this one is less clear.
This one is?
Is this less clear?
I thought at some point after the first step you were always obtaining Markov processes that were just slightly different.
Yes, exactly. But then I also construct, so I have coupling, stochastic. I think maybe it's a good idea if I'm not excited about it. So let's try to write a sort of sketch of the diagram. So we have a coupling phi n, which is actually the law of my diffusion with drift bn at time 0 and at time 1, right? This is my nth coupling. And then from this, I generate my stochastic interpolant n+1. So this is the random Brownian bridge, which is constructed with the coupling phi n, right? This is how I construct the interpolant from a coupling. Is clear? And you see that while doing this operation, this stochastic process here has lost the Markovianity, but has gained the fact that its bridges are Brownian bridges by construction. So this step here, you can interpret it, and you can even be more precise, but I cannot be now. This is a projection on the reciprocal class. And then from the stochastic interpolant, you compute the new drift. And this is the projection on the Markov. This I think we detailed better.
Is that the first margin is always right?
The marginals now, exactly. So the SBM has always had the right marginals. What is wrong is the correlations. The SBM always has the right marginal in the ideal setting in which you don't discretize. But having the right marginal, of course, does not mean that you're the right coupling. Okay, I want to conclude because croissants are waiting.
Okay, I tried this complicated analogy between the two, but why? Because actually it has been on for a long, long time.
I think even this probably goes to the 30s or 40s. That this is really old. That if you take the diffusion process, this is not super precise, but I want to give the idea. If you take a diffusion process, so imagine that this is the process to which the SBM converges after an infinite number of iterations. Since we keep alternating, the limiting processes has both properties. So it belongs to the reciprocal class. Meaning that its bridges are Brownian bridges. So P nu B, which is its own top space, xy equal to our xy for all x and y. Well, okay. And it fits the right marginals. So x mu b 0, x mu b 1 belongs to the coupling of the margin. Well, the theorem that has been known for a long time is that these two conditions characterize the Schrödinger bridge. Then you take the low. Here. Take the low. This is the Brownian bridge. Because actually people were interested in, okay, I have this mixture of bridges when they're Markov, when they're not Markov.
You're saying that it's Markov somewhere.
It's Markov because it's associated. So this is the kind of the moment I write like this, it's Markov. So of course, if we believe in this story, then the fixed point should have both, and it should be the Schrödinger bridge. Then, so first thing, one should really put this into solid ground, and then, okay, what about exponential convergence? Of course, this would be the difficult test, more difficult. Usual models. So the one I discussed yesterday, but of course, let me give you and myself a refresher. So we have our data distribution star. We have a partition of our time horizon. Now, capital T does not necessarily have to be equal to 1. It can be anything. And we have core approximation. And so capital T minus Tk for all k in between 0 and -1. And the algorithm that is okay. It's just a simulation, sorry, discretization of the time reversal of the noising process, what I call the forward process. So we start from the Gaussian distribution, which I denote by gamma. Then on each interval of the partition, I have my Orstein-Uhlenbeck part. Now again, I have a large time horizon, so I need the periodicity, so that's why I reintroduce the linear term, the dynamics. Then I have 2 times my core approximation that I compute at the leftmost extreme of the interval. This is my drift. And then I have the Brownian part. And this is true for all t in tk k plus 1. And the main question that people who try to carry out a theoretical analysis of these algorithms ask is, okay, now, if everything was perfect at time capital T, I recover exactly the data. Things are not perfect. I introduced many sources of error, as I've described yesterday. So how far is the low at time capital T of my algorithm from the data? So can I somehow bound in some metric or divergence that I generally call D, the distance between the low of my algorithm at time T and the data distribution? Can I bound it? Well, it turns out that under suitable assumptions, yes, you can bound this distance. And I want to state one set of sufficient conditions under which this happens. And this is also an opportunity to introduce Marta, because she has worked a lot on this together with Alain as well. And what I'm going to present now is issued from her work. So we need hypotheses, of course. So the first hypothesis we need is that we are able to learn the score reasonably well. So the first hypothesis is score approximation. So somehow here I'm decoupling. Of course, approximating well the score isn't a problem in itself. But it's not the problem I'm going to talk about now. I'm just going to assume that I have a decent quality of score approximation. And even if this is the case, it's really not over, as I said, because the fluctuations of the score are really complicated to understand. So what is a realistic assumption to put on the score approximation? Since you do this sort of empirical Monte Carlo, you cannot ask for too much. And the weakest assumptions that people have managed to consider, which also makes sense from a Monte Carlo viewpoint, is that of L2 approximation error. So essentially, you assume that you take the average error that you make in approximating score. The L2 error between your score approximation at time T minus K, which you compute in the forward process minus the actual thing we want to approximate. So this average here is less or equal than some tolerance epsilon spread. Just assume that you can do this. And once again, this is a reasonable assumption view of the Monte Carlo approximation of the score. There is quite some literature about how to verify this in practice, so we can safely assume that this is something that it's reasonable as an assumption. Also, the reason why I'm taking expectation under the forward process is also reasonable because samples from the forward process are the one we use to train the neural network that approximates the score. So that's a very reasonable law under which we can state our L2 bounds. Okay. And now we make another assumption, which is we need some regularity on data. And here I think we will have a small debate. So let me write down the assumption. I will assume that the feature information of the data is finite. And I recall the feature information is the N2 norm of the score associated with the data distribution. Of course, at this stage, it seems a bit strange because we've always been saying, oh, but the data distribution is empirical distribution, so why would you assume this? Actually, well, let me give you two answers. The first one is we could even do without, but somehow the proof would be very heavy, and I think it would kind of mask the interesting elements of the proof. But this is, let's say, not very justified from a mathematical viewpoint. The mathematical justification of this is that actually mu star is the real data distribution. So it's the distribution from which the data are sampled. So you use samples to construct the score approximation. And there you only have empirical distribution. This is why Alain was doing integration of partners. But if you recall, the idea is that these samples are drawn from a distribution that we don't know what it is, but there is no reason why this distribution should be wide. Actually, in some sense, you really don't want to sample again the empirical distribution that you use to train the neural network. In generative models, you actually want to produce new samples. You don't want to produce the same cat picture that you used to train the network. You want new cats. And what you try to reconstruct is a law that is kind of reasonable to assume that it's not too wide, which is the law from which the samples were drawn. But of course, for the training, you use samples. And in that case, yes, you cannot really make regularity assumptions. But it's reasonable to put some regularity assumptions. Okay. In fact, most of the papers assume even more, like some low concavity. But if you want, we can maybe elaborate more. I hope this is convincing. In any case, I think Alain has a even better view on this than I do. But this is how I explain myself the assumptions that we make. But okay, if you're interested, Martha can of course elaborate on this and tell you that we can even dispense with this and just assume that the data have second moment. Very enough, essential. And the theorem that I would like to is a theorem about constant step size discretization. So we don't do what we should do. So discretize a very fine mesh close to 0 and a very rough one close to capital T. And the theorem tells you that assume that you have H1 and H2, then you can bound the relative entropy between data and the law of your scheme with three terms. You have a term that accounts for first source of error, which was the initialization error. So e to the minus 2t entropy of R against gamma. This is you should think that this accounts for initialization, and the entropy is finite because if the feature is finite, the entropy is finite. This is log sum. No problem with this. Then we have the time discretization error and the score approximation. So the score approximation is epsilon squared times capital T. Somehow this is the error that we make with the score approximation. And then we have the Fisher information, H times Fisher information. And H is the constant step size, so it's just E over. So, initialization, the fact that I start with gamma, score approximation, the fact that I don't work with the score, time discretization. Okay. And as I said last time, these two are kind of okay, not very difficult to get these two, but it's kind of what is kind of tricky is this term. Right? All right. Are there questions about the statement? So before going into the actual sketch of proof, I would like to discuss again a little bit of time reversal, then discuss relative entropy for diffusions on path space, and then I would like to discuss what was probably my overreaching ambition at the beginning. I would like to discuss the fact that actually there is a deep connection between time reversal and stochastic control, which is exactly what will allow us to compute this stuff. So let's get back to time reversal, just to refresh. And reintroduce the backward process. So the backward process was just x backward of t is x forward of t minus. The dynamics were given by the time reversal. And I done some effort in order to write it in such a way that you have the ergodic term even time reversal. This is here.
So capital T is fixed, right?
It's fixed.
So the first term goes to 0 with n. How?
Yes, exactly. Okay, good. No, good question. Good question. So, in order, of course, at the end of the day, you want this to go to 0, and there is no other way to do this. So you must let capital T to infinity.
Oh, okay.
But of course, I mean, if you think about it, there is no other way, because as long as this is not really infinity, the initialization error will always be there. So you have to make time to infinity and discretization step to 0 and score approximation to 0 faster than t, and then it works. But somehow there's no reason to expect that you can. Actually, I think that maybe this calculation is actually sharp if you start, if your data is Gaussian, which of course it's not very meaningful in practice. But if it's a Gaussian that is different from gamma, from the invariant measure, I think this calculation is more or less sharp. But anyways, yes, it's important that in these models, to have, I mean, zero error, you need to let capture. Okay, so this is time reversal. And now I would like to discuss a little bit relative entropy on path space. And I'll tell you exactly what I mean by So it just gives you a statement. So the idea is that we will need in the proof to compute the relative entropy between the law that a certain diffusion process, not even diffusion, but that a certain stochastic process induces on the path space in comparison with the law of another. So take an index I equals 1, 2, and we let xi the solution of a stochastic differential equation in which I assume that the drift is not necessarily Markovian, so it's not does not just depend on the current position, but it can depend also on the past. This is because Euler schemes have a bit of delay in the definition. Okay, so I is the solution of the column SD. So I have a drift that depends on all the past. On all the past. I0 is no, let me call it mu I. Okay. The only difference with respect to before is again the drift may depend on all the past. But if you're perturbed by this, just think is xit. Doesn't matter. Okay. What do I want to do with this? I want to compute relative entropy of path space. So we call PI the law of the whole process. So it's a probability measure on the space of continuous path. Formula is if you compute relative entropy of P2 against P1, this is the relative entropy of M2 against M1. And of course, these relative entropies are computed for probability measures on different spaces. This is RE, and this is the space of trajectories. Plus, something that's quite funny. The expectation of the integral, 0 in capital T. I am, okay, maybe let me be more precise here. I am considering my load on the time window 0 T. And I get something that looks like kinetic energy in physics. So I get E2 minus E1 E squared x2 0 T. So you see that if I take out the expectation and I think that at least in terms of velocity, this is like some sort of kinetic energy. The average of the square velocity. The funny thing is that it actually coincides with relative path space. Is it
Inside there is x.
sorry?
Inside the parentheses is where x2.
Yes, excellent. Sorry, it's not very. I'll give the proof. So maybe it's gonna be. So the proof relies on a nice tool that unfortunately I cannot produce. I mean, not explain, but I will of course state what it is. It relies on Giordano's theorem. Okay, I have to start with Giordano. So Giordano theorem tells that gives us an expression for the radon-Nikodym density of P2 against P1, viewed as laws on the canonical space. So I will introduce or recall a bit of notation that I have used yesterday already. So I denote by omega t. This is the canonical process. So the canonical process on the canonical. So the Giordano theorem tells us that the density of path space computed on a path is given by the marginal density at time 0. So the margins are mu2, 1. If you compute in omega 0, and then you have the exponential marking, right? You have exponential of integral 0 t. Then you have b2. Now I will omit the dependence credit station b2 minus b1. Of course, they are computed on. Maybe I will write it just once. Then I think I'll maybe no, I will not hold it here. Minus, sorry, here I have to put a 2 because I have the square root of 2 there. Integral 0 t the quadratic. Unfortunately, I don't have so much space. I have to erase here. So this is an old theorem, but it gives us a nice expression for relative entropy. Because now relative entropy is what? Is the expectation of the logarithm of this taken under P2. Did I forget?
Why P2 minus P1, P1.
Why the difference of the square instead of the square of the difference?
Because I'm writing things on path space. So this thing does not have but simply because I mean I could write this as dp2 over Wiener times d of Wiener over dp1. So it's the quotient of the density against Wiener. And I will get the square in the end, of course, yes. So this is not over yet. I need to arrive here.
Okay, you should see. I don't see why this is.
So you probably would want to see the difference of the squares already here. Well, we will see. I think it should be okay, but let's see. So this implies that relative entropy of P2 against P1 is okay. I take the log of this and I integrate with respect to P2. But I think maybe I think the mismatch should come from the fact that for me omega is not the law of the solution of an SD, is really the canonical process. But okay, we will. So this is the relative entropy of mu q against mu1. The first term there is no doubt, right? And then I have plus the expectation. So I'm under P2. So the canonical process follows the law of the stochastic differential equation. So this is the expectation of 2 times the integral from 0 to t, d2t minus b1t. Of course, it should be computed on x2 on the interval 0t. I will not write this now, otherwise it gets too long. But I have to write the x2t. Then I have minus integral 0 to t square minus 1 square I continue. So now essentially I'm just gonna use the fact that this guy is equal to b2t t plus square root of t of 2 dbt. And of course, the expectation of a stochastic integral is going to be 0. So I can kill the term that comes from this. This is equal the expectation of now, since the expectation of the stochastic integral is 0, I only have dt terms in the integration. So I have 2 times b2t minus b1t inner product with b2t. Then I have minus b2t square plus b1t square with t. And so this gives me a, so this guy here is killed by 2 times this times this. So I only have a b2 square. So b2 square. And then I have minus 2 times b1 b2. Then I have a plus b1 squared that comes. And this concludes. Okay, so this is so why did let me tell you why did I do this calculation. I will but okay, right now probably it's not so motivating. Why did I do this? Because I want to use this board for intuition stuff. I want to bound the entropy between mu star and the law of my scheme at time t. But this formula kind of already shows that which is of course natural if you know a bit about relative entropy or the so-called data processing inequality, that the entropy between joint distribution is always bigger than the entropy between marginal distributions, right? So if you think a little bit about it, this is the entropy between the law of the time reversal at time t against the law of my scheme time t. But this is less or equal by the data processing inequality, or if you want, more or less by this formula, because you see that this is always going to be bigger than this one because this is negative. And the entropy of the law of the full distribution of space against the law the full distribution of space of my scheme. And for this one, I can use this expression here. Okay. But I will come to this at the end of the talk. But we are missing one ingredient for the proof, which is to understand a bit what does the score do. So what is the time evolution of the score? So I would erase here and present the last preparatory step. This is where I will not have the time to go into detail, but this is where the the relation with stochastic control will appear, and this is where I think there was a question about BSDs. This is where BSDs will appear. Somehow also viewpoint that is interesting for the study of other generative models. So as I said, we really want to avoid to look at pointwise bounds on the score. So let's look at the score as a stochastic process. What do I mean? You just define yt as now either you just find score process. And somehow what I would like to do is to compute its Ito differential. But it's not so obvious, right, to compute it. To compute it, it seems a bit. So my question is, what is the Ito differential? Right. And actually, it turns out that it's pretty nice. It's pretty explicit. So to do this, to compute this, I have to make to go back to PDEs again a little bit. So I will make some more definitions. We'll define FP as just this quantity here. So this is really a function. So EP so essentially, this is the evolution of the density of a constant process against its invariant measure. So it is very well known that it satisfies the Kolmogorov equation. This is like super classic. So I have VPSP plus Laplacian of FP minus I stands for the identity. So the identity I of x is equal to x. Gradient of FP and okay, f times capital P equals the density. Is the identity function. Well, that's right. Okay. So this is, of course, the Wolfgang-Uhlenbeck generator, right? Classical plus f equal to 0. And now let's make stochastic control pop up. So stochastic control just means optimization over stochastic. Familiar with this, but you will not need any stochastic control point of view. Now I define psi t. So I try to get closer and closer to the actual object I want to study, which is this. So I take the log. And now you can believe me that if I divide by FP here and do some tricks, I mean not some tricks, I mean just some calculations, I can get the PDE for psi t starting from the PDE expression. And the PDE for psi t turns out to be exactly what is the connection with stochastic control. Because it determines because you may recognize that this is just a very simple Hamilton-Jacobi band equation. It's telling us that actually time reversal is the solution of a certain stochastic control problem that unfortunately don't have the time to detail. But if you recognize the link with control immediately, then you already know how to write this down, because you say, but then my score process is nothing but the adjoint variable in a stochastic control problem, and I know I have my Pontryagin maximum principle, and I write down the dynamics. But I don't want to do that. I just want to do the calculation that kind of explains the dynamics of the score process. Let's first say the lemma. The lemma says simply that EYT is equal to YT dt plus ZT dt with YT equal to exactly the score times the score. And what is ZT? I have to say what is ZT. So ZT is times Hessian of log word and if you're familiar with control, you recognize here the joint process. But let's pretend we don't know anything about it. It's just the intercomposition of a process. This Z here is a bit mysterious, but luckily enough, we don't. All what I'm going to say next doesn't really care about what Z is. The super important thing is that I have a martingale term here. The rest we can forget, more or less. And somehow it's a backward stochastic differential equation because I have a terminal condition, not an initial condition. Okay. So if you put this together with the X dynamics, you get a forward backward stochastic differential equation, which is exactly the system. And I would just like to give you the gist of the proof. Long. Okay, so YT recall. So if you recall what is YT, okay, maybe this I can write it out. With a new notation, if the gradient of psi t computed in the backward times 2. So now we do some Ito calculations. So what is DYT? DYT is 2 times gradient of EP psi t. I always assume that I can exchange derivatives. Of course, I will not go into these problems now. Plus 2 times. So now you have to apply the generator of my process. But the generator of my process is exactly the diffusion with drift linear part plus y. So let's start with the Laplacian. And then let's go to the drift. So the drift has to be applied to the gradient of this function. So this is 2 times Hessian of psi t times 2 times, no, sorry, times. Oh, no, yes, it's 2 times the gradient of psi t minus x minus, let's say, the identity. This is the dt part applied to x backward t. Here you see immediately that I take in Ito, you take the derivative times the dbt part. So this you already see that this is zdbt. as a and ZT is exactly the process I've added. So now, we have to get rid of this ugly monster here. Let me just check. Yes, I didn't mess up with it. Okay, so here you see that it should kind of look like the gradient of this PD here. So we want to simplify terms by taking the gradient here. So let's do one thing here. Let's put these two terms together. Let me put a little dot. If I put these two terms together, I get exactly by the chain of the gradient of psi p square. So I can rewrite this whole thing here by taking out a gradient. I take one here, and one here. So it's 2 times the gradient of et psi p plus Laplacian of psi p plus the nonlinearity computed in x backward of t. Then I have not to forget this term here. So minus 2 Hessian of psi t identity is computed on x factor of e. And I will spare you so now. Thanks. Now, of course, I was not super smart because I've erased the HJB equation, but if you look here, we use HJB, implies that all what I have inside here is exactly equal to the gradient of psi p times the identity. And then you have to take another gradient here, so you will have an Hessian times the identity, which simplifies with this term here, and you will only be left with the other term, which gives you exactly what you want. So I will spare the detail. I think it's not important. The only thing which is interesting is that now you can use your HJB to do some product. Okay. So somehow the good message here is we don't really need to study the score as pointwise, but because it has a nice dynamics. That's an interesting point. It has a nice dynamics. And I think this is also time of date. Input. Oh, yeah. I would like to end by combining all of this and getting a sketch of proof for the theorem I wrote at the blackboard. So we start from here. Okay. I want to find the entropy between the data and my scheme, and I kind of obtain a trivial bound by considering the entropy of the corresponding laws of the corresponding laws of path space. And now I have to apply the formula for the entropy. So in order to apply the formula for the entropy, I need to associate to any of those two processes a drift, right? A drift. So let's do this together. So what is the drift? Let's call it P1. No, maybe let's start with this. This is the time reversal. So I use the same notation as in my lemma. I need two drifts, B2 and B1. So the drift of the time reversal is exactly what comes from the time reversal formula. So you have the Orsten limit plus the score part. Okay. So minus x plus the score part using the new notation. We wrote it like this, plus 2 times the gradient of Hamilton. And this is the Euler discretization. Maybe let me pick another color. This one. What's the drift of this guy here? Well, the linear part doesn't change. Okay. But then you have the delay, which is due to the Euler discretization. So this is plus 2 times this score at t minus, sorry, the score approximation at t minus tk. And then you have x, but this is not the current position, is the former position, time tk. Maybe to be more precise, this is p1 of x of the whole trajectory. And tk, of course, is the leftmost rim of the partition where I do my discretization. Perfect. So once this is done, I can, so once the identification of the formula is done, I have that the entropy between the law on path space of the backward, which I recall what you called it P backward yesterday, and this law, which I will define for convenience P star. Well, this is equal to the entropy of P backward at time 0 times P star times 0 plus the expectation. So here I would have the integral of the difference between the drifts, but of course I have this partition, so the integral will split into sums, right? So I have sum a running from 0 to 1. Yes. Of the integral between pk and pk plus 1 of the difference between, so I have to take the difference between this and that. So the linear part, they cancel out because they're just the same. So I have just this one minus this one. So 2 times gradient of E minus S star at E minus pk square computed, no, sorry, that's a mistake. I cannot compute them on the same. So this is computed exactly right where I am. And the score is computed in the discretization. So minus 2 times score approximation T minus tk computed at x backward. Okay. For this integral is b. Okay. Yes. But now something quite useful happens. So this guy here is exactly my y, the score profit. Well, in this guy, more or less, in the sense that it's an approximation. So here something could go well, let's say. And then let's also have a look at this term here. What is this term here? So the backward distribution at time 0 is the forward distribution at time capital T. This is the forward distribution at time capital T. And my scheme at 0 was initialized with a Gaussian. So this is gamma. This is the Gaussian. This is good because this calls for log sample. And here I want to use my hypothesis on the score approximation. See that the L2 hypothesis fits very well with computing the end. That's why I computed the entropy and didn't try another divergence, because it fits very well with the score approximation. So here I will add and subtract. So this is a good approximation of YTK. So plus minus 2 times 1. And if you do some, so this will allow me to use my hypothesis on the score approximation, because my hypothesis on the score approximation is exactly telling me that it has 2 sense, this and that are close. Okay. So if now I write less or equal with the tilde here to be less or equal to say less or equal up to constant. So what do? I mean, I add and subtract this term. I use the score approximation hypothesis here and a triangular inequality to get rid of this term. And I use log Sobolev here. Here I use my H. Okay. So log Sobolev tells me that this is less or equal than the entropy of the forward at time 0 times e to the minus 2t. But the forward at time 0 is exactly the data you start. Then I have plus the score approximation error. So here, essentially, on each partition of the time interval, I take an h, because I integrate epsilon square over h, and then I sum over n. H times n is equal to capital P. So the epsilon square t. This is, maybe I will color it green to say that it comes from the green part. This comes from the violet part. And then I have the so to say, difficult term. Plus expectation sum k running from 0 to n minus 1 integral tk k plus 1 norm of yt minus ytk. This is exactly or knowing the dynamics of yt. It's going to save me from having to make consideration on the regularity of the drift of the score viewed as a vector. Because what do I do now? So let's make some consideration. So these terms are nice. These are exactly the one that I needed. Theorem. Let's make some considerations. So in here, t minus tk is less or equal than h, because t is in between the partition. The h is more. Because you can imagine you're taking a fine discretization. So you recall that yt, if I do some discretization, is of the order, so is ytk times t minus tk. So I do some sort of discretization of the dynamics of yt that I found with the two. Plus z K E T K minus. So this is just, sorry, maybe I should have been told that. So this is a different mistake. This is not YT minus YT. This is just a discretization of the formula that we found, that dyt is yt dt plus z. Short time, just discretize. So let's see who is the bad guy in this decomposition. Of course, the bad guy is the martingale term, right? Because this term here, t minus tk is not no larger than h. So this term here is of order little h. But this guy here, so this obviously the Brownian fluctuations. In short time, they dominate the dt fluctuation. This is a heuristically ordered square root of h. Okay. So in short time, we can think that this term doesn't exist. Of course, it's an approximation, but I don't want to do all the calculations because that would be a bit cumbersome. And the nice part of the proof is exactly what you get by dropping this term. So again, we are trying to understand the fluctuation of fluctuations yt in short time. Of ito processes in short time essentially is the martingale part that gives fluctuation. The deterministic part is not very. So let's pretend. So let's cheat actually and pretend that this is true. Want to cheat? This of cheating is right for people. So we pretend this is true. But then, if this is true, something gets pretty simple here. If some of you maybe already sees why. So now I use maybe better. If we cheat, of course, it's not too much of cheating in the end. Essentially, I'm saying that yt is a martingale. So now, suppose I have to estimate. That's exactly what I have to do. The square of the increment of a martingale. So there is this nice thing that for martingales there is like something people call, maybe it's a bit too emphatic, but so the Pythagorean theorem for martingales. So the expectation of the square of the increments is the difference in the expectation of the square. This is of course only true because we have martingales. But then yt is a martingale means that yt square is a sub-martingale because convex function of martingales are sub-martingales. So the expectation is increasing in time. So this is less or equal. And the expectation of this thing square, because t is less or equal than tk plus 1, minus this. Again, basic properties of martingale, orthogonality of the increment, and convex function of martingale or something. And now we're done because This was the object that we wanted to estimate. And I estimate each of these expectations here uniformly for t in between tk and tk plus 1 with this term here. So I pick up, so let me call it asterisk. I pick up an h because I integrate over the tk plus 1 and the length of the mesh of the partition is exactly h. Then I have something kind of cute because this is the expectation. Sum k running from 0 to n minus 1 of ytk plus 1 square minus ytk squared. But this is a telescopic sum, right? So in the end, this is actually equal to h times expectation of y capital T squared minus y of 0. Okay, y0 squared is of course positive, so this is less or equal than h times this guy. But what is yt squared? Yt squared is the Fisher information, because if you recall, yt is the gradient of the log of d mu star against the gamma, and compute, sorry, in x backward of t. But x backward of t follows the law mu star. X backward of time t is the data. So this guy here is exactly, well, as usual, no, sorry, there is a 2, but okay, doesn't matter. Oh, so there is a 2 here. So up to multiplicative constant, this is times h. And that's how the proof more or less works. Or no, I would like, oh no, maybe, okay, so that's over. No more proofs. But there's much more than one could say. For example, can we analyze similar things for or Riemannian manifolds for kinetic samplers and millions of things? But I think it doesn't make much sense to go into this here. So I think maybe I'll just conclude by thanking again all the people who invited me and Alain here to give this course. We were both very happy, and I hope somehow the message went through. And thanks again. It's over.